Welcome to the discussion of normal probability distributions. This is going to be kind of the building block backbone of all inferential statistics. So you want to make sure that you really understand what's going on here. You need to get a good handle of the normal distribution curve and the properties of it and the different things we can do with z-scores, and all of this will lead into confidence intervals and hypothesis testing and all that stuff. So really make sure you spend some time on this section. Okay, we all know what the bell curve is. We've heard it discussed a million times, and this is just a nice, pretty picture of it. Over here is the formula for this blue line, right? That dark blue line is actually a function, and this is the formula that creates that function. Don't worry, you're not going to have to use that. It's just in case you were curious, that's where it comes from. Some of the key concepts of the normal curve is that it's bell-shaped, duh. Its mean, right, is equal to 0, and the standard deviation is equal to 1. Now that's only if we're talking about the standard normal distribution, right? It has to be standardized. If it's standardized, then you have these properties. We can have normal curves without those properties, and they're just called normal curves or normal distributions. But to be standard normal, they have to have those two properties. So we're going to start off talking about the standard normal curve, and then we're going to learn how we can use the same properties with any normal curve, and we can actually, quote unquote, standardize it with a very simple formula. Okay, a density curve is just a graph. It's like a histogram for a continuous probability distribution. So before, when we were talking about our probability distributions, we were talking about discrete random variables, right? Things that had gaps in between them, usually counting numbers, 1, 2, 3, 4, 5, that kind of thing. Well, now we're going to talk about a probability distribution function for a continuous random variable, and therefore we get a continuous probability distribution. And instead of having jagged bars, on a histogram, we get this nice smooth bell curve. The total area under the curve must equal 1, just like with our normal probability distribution, that all of the probabilities have to add up to 1. So all the area under those bars had to add up to 1. Now all the area under the curve has to add up to 1. So if the mean, mu here, right, if that mean is right there in the middle, then how much area is to the left of that? And you can say 50%, right? So we're going to use this idea of 100%, or the area being 1 under the curve, to be able to answer questions involving probabilities. Every point on the curve must have a vertical height that is 0 or greater. That just means that the curve is always above the x-axis. And you can see from the picture that that's what it looks like. And these tails on each side, even though they get really, really super close, they technically never touch. They go on forever, but they get so thin that the area does, in fact, end up having a bound. It has a limit, and its limit is 1. Because the total area under it is 1, right, we can very easily make this relationship between area under the curve and probability. So if we come along and say, hey, between this x here and this x here, we can call it x1 and x2, if we calculated this area, and that area ended up being 0.23, then that would mean the probability of picking an x that was between this x1 and x2 would equal 0.23. So this normal curve is going to represent some sort of experiment, like maybe these are the heights of adult males, and x1 here is 50 inches tall, right, and maybe this is 58 inches tall. And so this is saying the probability of picking one adult male at random and finding out that that person is between 50 and 58 inches tall is 0.23, or there's a 23% chance, right, that a person would be between those two heights. That's what's going to happen with these types of questions. Oh, and by the way, the same would go for 50 strictly less than x strictly less than 58. Because the only difference between these two is one counts the line and one doesn't count the line, but there's no area involved in a line, right? It's area under the curve, right? Area is related to probability. And so there's no area for a straight line because it has no width. So the difference between a strictly less than and a less than or equal to means nothing, which means now if we said what's the probability that x equals 50, it's going to be 0, right? We're no longer going to be able to have questions where someone is actually equal, right? So it can't be equal to something. It has to be a range of things. Because in order for us to have questions where we're looking for x to equal an exact number, we have to go back to our discrete random variable and do our discrete probability distributions that we did in previous lessons. Now we've moved on to continuous, so we no longer ask questions about our random variable equaling an exact number. It's always going to be a range of numbers. We're going to start off understanding this concept by looking at a uniform distribution. And a uniform distribution is exactly like it sounds, where all of the probabilities are uniformly distributed, i.e. The range of probabilities for every single value of our range of values for our x, our random variable can go from, let's say, 0 to 5. All of those particular values have the exact same probability, and what happens is you end up getting a nice perfect rectangle. So here's an example. So given the uniform distribution illustrated below, and this is for voltage levels, they measured voltage levels on some sort of circuit, and they found that the voltage levels on that circuit ranged between 123 up to 125. And because it's a measurement of a measurement of a quality, you can get all of those things in between. You can get volts of 123.1, 123.001, etc., etc., etc. And because it is a uniform distribution, that means that at any particular given point in time, the circuit has equally likely probability of being any of these voltage measurements from 123 to 125. If you look at this distance, right, from 123 to 125, that's a distance of 2. So in order to make this probability distribution be accurate, remember that one of the number one rules was the area under the curve has to equal 1. So that's why the height is 0.5, right? Because 0.5 times 2 gives you a total area of 1. If we look at this shaded region from 124.5 to 125, that's a distance of 1/2 times a height of 1/2. That's an area of 0.25. So that means that the probability of the voltage, right, being greater than or equal to 124.5 equals 0.25. And that's all we're doing with these things. This is really easy because we can just do geometry. But what happens when we have a curve that looks like this? And we want to know what's the probability that we have values between 1 and 2. Well, you can no longer use geometry to find that area. But if you remember from the previous slides, from the first one, we do have this lovely formula that gives us the function, and so we can actually find the area under the curve using integral calculus. Now luckily we don't have to do that, because since this curve is a standard normal curve, it always has the exact same shape. It always has the average is 0, the standard deviation is 1, so the shape of that curve is exactly the same every single time when we have a standard normal, and therefore we only needed to find the area under it once, and then we could put all those numbers into a table, or slap it into that formula into technology, and then the technology can always find the area for us. So we don't have to use that formula. Technology and tables can do it for us. And that's what this says, but like it says in red, we strongly recommend using technology. Tables are great. They're easy to use. Don't get me wrong. But we have technology, so why not use it? Because technology will give us a more accurate answer than tables. Tables always round off here and there. Here's some of the notation that you're going to see going forward. The first one just means we're looking for the probability that a z-score is between A and B. The second one, greater. The third one, less than. Now, I failed to mention what a z-score is. Let's go back here and look at z-scores are just these distances from the mean. Remember that the mean is always 0, and a z-score just tells us how far we are from the mean in either a positive or negative direction. This normal curve sits on the number line, so this is sitting at the origin of 0. So a z-score is exactly a distance of 1. Right, a z-score of 1 is exactly 1 above, and then 2 and 3, and so on and so forth. And you'll notice that pretty much all of the area is in between 3 plus and minus, right, z-scores. There is a little area beyond it, but it gets so small that it tends to 0. All right, methods for finding the area. Now you're going to have two different types of questions. You're going to have a question that's going to just say how much area is above z and below z, which is what we call one-tailed, right? These are going to be one-tailed tests we'll talk about later, but you're looking for area just in one direction. And then this one is you're looking for area in between two things, so it's kind of like a two-tailed test that we'll do later. When you're doing either or, if you use the TI-83 or Statcrunch, or the TI-84, right? Any of the TI calculators, and in fact the 86s, 89s, and the TI Inspires, and all the fancier ones that go above and beyond those will do it as well. Just the menus might be slightly different. I'm always going to show you how to do the menu on the TI-83 because I told you how to get that nice free emulator, so you can run the TI-83, 84 on a PC, Mac, or Android tablets for free. And so I'll always use the TI-83 whenever I do calculator examples. Statcrunch is that really easy to use proprietary software that you can do online that you either have to pay for or you get it free if you're in the right kind of class environment. Minitab, there'll always be Minitab examples, and Excel whenever I can, because most people have Excel and some people have Minitab. Okay, so as you can see, the menus used for all of them are hugely different, so you just need to pick a technology that you like and kind of stick with it is the best piece of advice I can give you. I personally would do, my first choice would be Statcrunch. If you're using the Pearson My Math Lab, My Stat Lab stuff, because it comes free with that and it makes it very easy to use. If you're not, then I would do the TI-83 because again you can do the free emulator and it's pretty easy to use. Okay, so these are the commands. Let me just show you really quickly the TI version. So here's the TI emulator. You hit the second button and the vars for variables. This brings up this menu. You can see right here number 2, normal CDF. So you can either arrow down or just hit number 2. Enter, and what you need to do is give it your two z-scores separated by a comma. So you're basically giving it the lower and the upper. So let's say we do a -1, and remember to do negative, you got to use the negative symbol. -1, comma 1. You don't really have to close the parentheses, but it's always nice just to be sure. Hit enter, and this tells you that between -1 and 1 as z-scores, you've got 0.682 blah blah blah, so a little bit more than 68% of your data. And if you remember the 68, 95, 99.7 rules that we talked about before, If we go one standard deviation in both direction on the normal curve, there's supposed to be 68% of our data, and here's 68% of our data. So you might be hopefully making the correlation that z-scores are standard deviations, right? A z-score of 1 is 1 standard deviation above the mean. A z-score of 2 is 2 standard deviations above the mean. So if we did this again for minus 2 to 2, what should the answer be? 95. Seeing it's not exactly 95, and I told you before those are approximations, those 68, 95, 99.7s. Okay, Statcrunch, just as easy. Let's take a look at Statcrunch here real quick. Okay, so here is your Statcrunch page when you open it up. What you want to do is go to Stat, Calculators, and then Normal, because we're dealing with a normal curve. That brings up your new little window. And the thing that's nice about this is it gives you both options. The standard option, as the picture implies, gives you area under the curve, up to a certain point. So right now they're letting, and they're saying x instead of z, right? So they're using x's instead of z's. So right now, if we go from all the way to the left as far as it'll go up to 0, you can see that we get half of our data, or 50%. If we wanted to go to 1, hit compute, that gives us 84%. Now if we wanted to go in between two things, we just click on the between button, and now you can see between -1 and 1, there's that 68 that we got in the other example, and -2 and 2 gives us 95. Okay, very easy to use. I won't spend time going through Minitab in Excel. The Excel ones are pretty easy to just read and try yourself if you like to use Excel. Here is the table I was talking about, and you'll find a table similar to this in any stat book that you use. You can find them online all over the place. These are always cumulative areas. As you'll notice up here, it says cumulative area to the left. I recommend drawing a picture. What this means is if this is your curve and this is my z, it's giving me all the area from the left up to that point, right? So if we wanted to find the area up to, let's just pick something that's on the negative side so we can actually see it on this table. So here's my negative z. Let's say it's negative 1.85. See, and that's the problem with these tables, is you can only go to 2 decimal places. So to do negative 1.85, here's negative 1.8, and then here's the 0.05, right, the second decimal. So you do the intersection of those two, and you get this value right there, and that tells you that the area to the left of that, right, all in here, is 0.0322. And again, the problem with the table is it only gives you 4 decimals, and if you remember from the calculator and Statcrunch, we got 10, 12 decimals, and in fact we had even more decimals. It's just those are the only ones that it displays on the screen. So the tables are far inferior, but it's something that we have to use if we don't have technology. But you should all be able to do technology. This is just helping you walk through how to use tables if you want to go that route. I would recommend using technology. So you can go through these steps. Pay attention, please, to this step. Whether you're using technology or not, I really suggest drawing a picture every time, because then once you get an answer out of technology, you can look at your picture and ask yourself, does it make sense? Because it's very easy to type something into technology wrong and then get a wrong answer. So always draw a picture regardless of whether you're going to use technology or a table. Here's an example. Bone density. And they're telling us that bone density measurements are normally distributed with a mean of 0 and a standard deviation of 1. So yay, they're standard normal. A randomly selected adult undergoes the test, and they want to find the probability that the result is a reading less than 1.27. So what they're really asking is, if we had a normal curve and we had a z here, right, that was 1.27, so there's the average of 0, so we're obviously on the positive side. Find the probability that the result is a reading less than that, right? So we're looking for all of the area below it. So right off the bat, is this answer going to be bigger than 50% or less than 50%? And hopefully you're all going, it's bigger than 50%. So that will help you to kind of double check and make sure you didn't make a boo-boo with your technology. So this is what we're looking for. We're looking for the probability that Z is less than 127, right? We're looking for all of this green area. The table gives us 0.8980. If we were to do technology, well, you'll remember when we did this one, right, and when we did Statcrunch, it had the option where we could do either the standard, where it gave us something below a point, or we could do in between. But this function on the calculator always just does in between. So if we're doing in between, how the heck do we work with just below 127 or 1.27? Well, that's really easy, because all you have to do is set the lower, right, because this wants lower upper. You just want to set the lower to be basically off the charts, right? Whatever, as far as it can go to below. So just do negative 1,000 and then comma 1.27. Look at that right there. And 0.89795 blah blah blah, it would round up to the exact 0.8980. And if you try bigger and bigger negative numbers for your first one, so how about negative a bunch of zeros, comma 1.27, didn't change at all, right? It gets to a certain point where there's just really no area out there in that tail. So normally 1,000, negative 1,000 is big enough. You could do, negative 9999, same number of digits and even bigger. You'll be fine either way, because we're normally going to round our answers to 4 decimals, so you're going to get the right answer either way. Okay, so technology, even this one works really well. You just have to know that when you're doing lower and upper, and you're actually just trying to find something below or above, then you just turn the lower or the upper into a really, really big number. So if we wanted to find the probability that Z was bigger than 1.27, we could do this exact same thing, but we would do 1.27 comma positive 1,000 or positive 9999. And then it would give us this area over here on the right. Okay? Here's how they found it in the table. So this is just summing up that this answer of 0.8980 is telling us that's the actual probability of choosing one random adult and having their bone density less than 1.27. Using the same bone density test, we could find the probability that a randomly selected person has a result above negative 0.1, which is considered to be the normal range for bone density. So, what's the probability that somebody is quote unquote normal or has normal bone density? So let's go back to the calculator just to remind ourselves and make sure that we're all okay with this, that if we wanted to do it this way, second vars, number 2, and now we're going to go above, right? So our lower bound is the negative 1, and our upper bound, I'm just going to do 9999. And there's the 0.8413. And we didn't have to do the math. See, to do the tables always give you area below. So you would have to look up negative 1 in the table. It would give you 0.1587. See, because it gives you the area below. And then you have to do 1 minus it, because the total area is always 1, right? So this ends up being the complement. So it's 1 minus it. And you get that same answer of 8413. So there's an 84% chance, or a little bit more than 84% chance, that anybody that you choose at random will have a normal range of bone density. And we can go through these examples. It's the same thing. If you wanted to find the area in between two, If you had to use the tables, you'd have to go this route where you'd find the area below -1, the area below -2.5, and then you do the difference between of the two to find the area in between, right? Because from -1 down gives you all this area, and then from -2.5 down gives you that area, so the difference between them gives the area in between. But obviously we would just use the calculator and put that, -2.5 as our lower bound, -1 as our upper bound, and we'd get the answer much easier than tables. Okay, now we're going to work in reverse. So before we found the area under the curve when we were given a z-score, now we want to find the z-score given areas. And as I said before, always draw a picture. That's always the first thing you want to do when you're doing these things, is draw yourself a picture and identify the area that you're looking for, and it just helps you to not make any silly mistakes, and it gives you a really good check to make sure that your technology gave you the answer you're looking for. So here's the question. What z-score puts us in the 95th percentile, i.e. what z-score puts 95% of the area below us, and thus 5% above. Now you could look it up in the table. You could go to the table and start looking through all of these things and try and find where is 95, and you go, well, here's 0.9495, here's 0.9505. It's got to be in between, and so that means it's 1.645, so it's in between those two, so you do 1.645, right? And that's what they did here, 1.645. But just like the other things, technology can do this, and it can do it better and more accurately. So I'm going to clear this, and once again we go into second vars for our variables, right? And you'll see number 3 is the inverse normal, because we're doing the inverse. We're kind of going in reverse, right? Inverse. Now the inverse normal wants you to type in the area under the curve and then comma the mean and the standard deviation. Now if you're using a standard normal curve where the mean is 0 and the standard deviation is 1, you can leave those parts off and it just uses the standard normal. But you can also use this for other curves, as we'll have other examples later. So let's just do 0.95, and you'll see that if I don't put comma mean, comma standard deviation, if I just give it this, it assumes the 0 and the 1, and voila, there it is, 1.644 blah 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 blah. Much more accurate than 1.645, but it would round to the same thing if we actually rounded to 3 decimals. Here they're using the same bone density test for another example. Instead of finding the 95th percentile where you have 95% below, they want to find the z-scores that put 95% in between them, and then have the 5% split between the two tails, so 2.5 in each tail. Now if you remember the 68, 95, 99.7 rule, you know that roughly 2 standard deviations out gives you 95% of your data. And you can see from their results that roughly 2 means plus and minus 1.96. And again, they got those from the table. But technology is much more accurate. If we want to find this upper z-score here, we have to find the z-score that gives us how much area below. And the answer is not 95, because remember, the area below this is the 95 plus the area that's in that tail. So it's actually 0.975. And there's the 1.95996 blah 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 that they rounded up to 1.96. And if you wanted to find the lower one, you would do the same thing, but you would just put in the 0.025 and it would give you the negative. But since z-scores are symmetrical, right, we don't need to do both. We can just find one, and we know the other one is the opposite, right, the negative of it. That's if we want symmetrical error. If we wanted, something that wasn't symmetrical, it'd be completely different. But usually we're always looking for symmetrical area. A critical value are these z-scores that we've been finding. A critical value is the name that we give to the z-score that cuts off a certain amount of area. So when you see z sub a, and that's z sub alpha, sorry, when you see z sub alpha written somewhere, that's denoting this z-score that has alpha area to the right. So in this example here, that would have been z sub 0.025, right? That would be that z-score there. And then this z-score there would be z of 0.975, because that's how much area it has to the right. We normally do alpha to the right. We can sometimes, when we get into further examples, we'll do just z of alpha to the extreme. So how much area is to the outside of that cutoff. So in that case, if we were doing that, then the z on the left would still be the same thing. It would be z of 0.025, because that's how much area is out here in this rejection region, right? The area to the left, to the outside of that cutoff. But normally it's area to the right. Normally we only deal with the upper z, the z to the right, and then if we need one on the left, we know it's just the negative, right? 1.96 versus negative 1.96. So these critical values are these cutoff points where we're trying to say we're looking for things within a certain boundary, and that boundary is that critical value. So when we ask for z critical, that's what we're asking for. Finding the value of the z of the 0.025, we already did that. That's the 1.96, right? It's got 0.025 area to the right. Now we're going to move on to applications over these normal distributions. We're no longer going to be talking about the standard normal. We're now going to see how can we do this same type of idea, but with things that have a normal distribution that no longer have a mean of 0 and a standard deviation of 1, right? So in these cases, we no longer have the situation where the mean is 0 and the standard deviation is 1. But that's fine. They're still normal curves, so they still have that symmetry. They still have that 68, 95, 99.7, distribution of area. They still have the total area equals 1 underneath the curve. But now, when we go out one standard deviation in each direction, it's no longer exactly 1, right? With the standard normal, a standard deviation was a distance of 1. So when we went out one standard deviation, our z-score was 1. Well, now, if our standard deviation is, let's say, 3, and we go out to that z-score of 1, that one standard deviation, we've actually gone a distance of 3 points, but it's still a standard deviation of 1, so it's still a z-score of 1, right? The z-scores correspond to how many standard deviations we are above and below, not how many actual points or distance or anything like that. It's in standard deviations. This is going to be our conversion formula that's going to take any normal curve and give us the same z-score version on that, that we would have for a standard normal curve. All it's doing is it's taking our average that we have, it's taking our data value, subtracting our average from it, so it's giving us the distance between our data value and the mean, and then dividing by the standard deviation, and it's telling us how far our data value is from the mean in terms of standard deviations. Well, that's what a z-score is, right? If you're on the curve, oh, that's a horrible curve. Let's try a better one. Let's go over here. If you're on the curve and you're over here, so here's our average, right? Here's mu, and we want to figure out how far x is from mu. We take this distance and we divide by the standard deviation, and it tells us how many standard deviations we are above, and that tells us what our z-score is, because a z-score is just the number of standard deviations. So whether we are dealing with a normal curve with a really small standard deviation, right? It's really narrow, everything is clumped together, or a really large standard deviation where it's wider and more spread out, it doesn't matter which one we have. Once we use this lovely formula, we've now standardized it, and all of this data is now represented by the standard normal distribution curve, and we can do all the same wonderful things we did before with figuring out probabilities under the curve by figuring out z-scores and blah, 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 blah. It's very, very easy. Now, the procedure that the slides are going to walk you through is assuming you don't have technology. First step is still the same whether you have technology or not. You always want to sketch the curve, label your mean, right? And then label the thing that you're looking for, the x values or whatever, and then shade in the region that you're trying to find. Doing all of that just gives you an idea of what you're looking for, and again, it gives you that idea of, am I looking for something that's bigger than 50%, smaller than 50%, so you can kind of double check that your technology didn't give you the wrong answer. Okay, now the rest of this is going to say you can use tables or software or calculators, whatever you always try to use technology. Technology is the way to go. So let's look at an example. So Tall Clubs International, right, has a requirement that women must be at least 70 inches tall. Given that women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, find the percentage of women who satisfy that height requirement, i.e. what percentage of all women would be allowed into this exclusive tall club. Here's my picture. Always want to draw a picture. Now the average, right, your mu for a standard normal is 0, but for us it's 63.8, right? They told us an average of 63.8. And our standard deviation, and I know that looks more like a delta, but that's my sigma, right? That's my yoink. That's standard deviation, is 2.6 inches. So if I went out here to a z-score of 1, right? If my z-score equals 1, then what height would that be, right? What would the x value be? Well, it would be 2.6 above, so 63.8 plus 2.6 is 66.4. That would be a height of 66.4. And we could do this all day long, right? Go out 2, go out 3, etc., etc., etc. But we want to know, we're looking for the women have to be at least 70. So they got to be out here at 70, and they've got to be at least that tall, right? So we're looking for the probability, right? The amount of area to the right of 70. And we want to figure out what that area is. Okay, two different ways. Let's take a look at Statcrunch first. So we want area above 70. So let's go to standard because this gives us area in one place. So our mean was what was it? 68.2, I think. Nope, 63.8. Boy, I got a horrible memory. 63.8. Let's try that again. 63.8. And our standard deviation, 2.6. And we want to know what, how many are above a distance or a height of 70. So if we put in 70 here and compute, look what happens. It changes the curve. You can now see that the average right here in the middle is at 63.8. The standard deviation has been shifted to 2.6. So our scale now is down here at 60s and 70s instead of the -1s and +1, 2. The probability that x is less than or equal to 70, and you can see it's shaded in here in red, gives us 0.99145, blah, blah, blah. But we want the stuff above it, right? So all we have to do is 1 minus that. So if we went down here and did, equals 1 minus 0.99145, it doesn't work. This isn't the same thing as Excel. It doesn't work that way, unfortunately. So you'd have to do this in your calculator or by hand, but you can see that it's going to be 0.00, let's say 85 if we round, 0.0085. According to Statcrunch, we get 0.0085. What about if we wanted to use our calculator, our nice calculator emulator? In this instant, we're trying to find area under the curve, right? We're given an x value and we're trying to find area. So are we going to do the inverse norm, or are we going to do the other one, the normal CDF? And the answer is normal CDF, because that's the one that we give it lower, upper, right? And it gives us area in between. But what I didn't tell you is we can also give it lower, upper, comma, mean and standard deviation, and it'll give us the answer for a non-standard, right? So what's our lower going to be in this case? 70, because we're looking for everything from 70 and above. What's the upper going to be? Well, we're looking for something off the charts, so just give it a really big number, 99999, comma, the mean, 63.8, comma, the standard deviation, 2.6. Close the parentheses, hit enter, there's your answer, 0.008548, blah, 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 blah. The same thing we got once we rounded Statcrunch. So these calculators are our lifesaver, guys. Really get to know how to use them, and it's going to make your life so much easier. If we wanted to find the height that put us at a certain point, that's where we would do the inverse normal, right? But in this case, we're given a cutoff, an x value of 70, and trying to find the corresponding probability. So that's where we do the normal CDF. Okay? That's how technology will do it. This is how they want you to do it. Draw a picture, shade in the region, which so far so good. That's what I want you to do. But then they had you calculate the z-score using the z-score formula of z equals x minus mu all over standard deviation. So in this case, our z would be 70 minus 63.8 all over, what was it, 2.6. That, if you work it out in your calculator, gives you the z-score of 2.38. And then you could go look up 2.38 in your tables. That would give you the area to the left, which would give you this number. And then you do 1 minus it to finally get the answer. Now you notice their number is slightly different from ours because the table rounds, right? Everything gets rounded differently. Our answer of 0.0085 is actually the more accurate of the two. Procedures for finding values from known areas or probabilities. This is what we did before, where instead of saying, how many people are above a height of 70, they're going to give us a percentage and ask us to find those cutoffs. We still want to draw that picture. We always want to sketch that picture and figure out what we're doing, right? Give ourselves a little picture. Then, according to this, we want to use technology, or try and work backwards with the table. That's just a pain. You don't want to do that. So use technology. Here's an example. When designing aircraft cabins, here's an example. When designing aircraft cabins, what ceiling height will allow 95% of men to stand without bumping their heads? Men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. So the first thing we do is we draw that picture. So there's our normal distribution. Then we label everything we have. There's our mean, right? We probably should have labeled our standard deviation somewhere, just so we have it. We don't have to look back at the question. And we want to figure out what x value, right? What height cuts off with 95% of the area below it. So if you're that tall, you're in the 95th percentile, right? And if they set the cabin height to be that high, then 95% of all adult males would be able to walk around without bumping their heads, and only 5% would be tall enough they'd have to duck. Now, if you look up in the table what value has 95% of the area below it, you might remember from a previous example, it's 1.645. And then from there, they want you to go and plug it into the formula. Z-score equals x minus mu over standard deviation. plug in what you have and solve for what you don't have. So 1.645 equals x is what we're looking for, minus 69.5 all over standard deviation of 2.4, and now solve for x. It's not too bad. It's a pretty easy algebra, right? Multiply both sides by 2.4 and then add the 69.5 and you'll solve for x. It's not bad at all. In fact, if you do the math, it ends up being 73.448. No, I'm not Rain Man. I have that written down. I've done it before. That's what you get if you use the formula. But let's do it with technology. And I always like to use the calculator. I just think it's the easiest. Okay, so in this case, we're given area under the curve, and we want to find the x that gives us that area. So are we doing normal CDF, or are we doing inverse norm? And hopefully you're all going, oh, it's inverse norm. Of course it is. Stop treating me like I'm a moron. I get it already. Okay, good. It's inverse norm. Do you remember what we put in for inverse norm? The first number is the area to the left, 0.95, comma. The second number is the mean, in this case 69.5, comma. The third number is standard deviation. You'll kind of notice that whenever we're dealing with these types of things, it's always mean and standard deviation at the end. 73.4476 blah 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 blah, which of course rounds to 73.448. Same thing, a lot less headache. Here it is worked out, right? Like I told you, if we did it by hand, that's what we would have gotten. Same thing. And that's the last example that we're going to do working with standard normal curves and now non-standard normal curves. So everything's the same, right? We still draw a picture. Number one, draw a picture. And then whether it's a question of here's my x, what is the area, or here's my area, what is my x, either way, right? They give you the area and they want you to find the x, or they give you the x and want you to maybe find the area in this direction. It doesn't matter. You just use technology one way or the other, right? We're either using the inverse norm if we're given area and want to find the x. We use inverse norm if we're doing the calculators. That finds the x given the area. Or if we're given the x and we want to find the area, that's number two, the normal, I think it's just normal CDF is what it's called. So those are the two calculator ones that we use. You can obviously do the same thing very easily with Statcrunch, Excel, Minitab. There's a lot of different ways to do it with technology. That's it.